By now, you must be convinced that the Turing machines are quite powerful as devices that can implement algorithms. We have seen not just the basic model of Turing machines, we have seen several extensions, that is adding of some extra power or facilities to the basic machine. And we have found that even with added power, the class of languages which would be accepted after, for example, an extra tape is added, something like that, that class of languages which can be accepted by Turing machines, that class remains invariant. Before we study the limitation of this class of languages, which we had called recursively enumerable class of languages, I would like to emphasize again that Turing machines are very powerful devices, although they look very simple. By now, if you think a little, you should be convinced that Turing machines can simulate computers as we know. Let me just spend a couple of minutes on this point, that now when we say Turing machines can simulate computers, what we would like to say is that suppose you are carrying out an algorithm by means of computer as you know, that particular algorithm can also be carried out by a Turing machine. So, to convince you of this statement, what we can do is to consider a very simple processor. Now again, I would like to emphasize that just because I am considering a simple processor, I am no way limiting the scope of this particular statement, because even a simple processor can simulate, that is known, fairly or however elaborate processor that you might think of. So, what is a processor? Simple processor that can be modeled this way, that a simple processor of course executes programs, it has memory, and this memory contains both data and the program, right. And a simple processor can have some registers, and registers also can store some bit pattern, right. So, we are just talking of simple processors. All right. Now, from our knowledge of computer organization, we know how does a simple processor operate. Because what it does, that at any given time there is some contents of program counter, which is a register. Now, program counter tells us which instruction is to be executed next. And of course, program is a sequence of instructions. It can be, of course, the execution of a program, how it will execute, in which sequence these instructions will be executed, that can depend on data, etc. That all we know. But basically, there is some place which has the address of the next instruction, right, to be executed. And then of course there is memory. And what is the essential part about a memory? That every memory cell has an address, and in that address that cell at that address contains some bit patterns, right. So a typical instruction could be like add, okay, M1 and M2, M3, something like this, right. This instruction is telling that add the contents of memory 1, cell 1 to memory 2, and the result should be placed in memory address 3. Right. So one way of doing all this by a kind of machine that we have, by machine I mean a Turing machine that we have, we can imagine our Turing machine has several tapes, and one tape contains or models the memory. That models memory. Right. And this also we may have, may have another tape to do work, etc. We can say work tape. Just consider how an instruction like this could be added. First of all, we need to say a little more about what we mean by modeling memory. So we may say that we have some special symbol followed by a string, and then again this special symbol followed by some string, and then again here let us say in between I have a cell which also contains another special symbol, let us say all right. So imagine this. Now what I will interpret, that this part is the address, after all address is a string, and this part between sent symbol and the next sharp symbol is the, we are saying what would be the contents of the memory cell whose address is this. Now of course in normal day-to-day processors we have some bound which is the word length, etc., that kind of situation. But here in this model we can have arbitrary sized contents, right. So now an instruction which is to be executed, which is like this, let us say, which will that these parts of the instruction will tell me 3 addresses, right. So imagine that here I had the contents of the addresses, all right. So M1 is an address, M2 is another address, M3 is another address, right. All right. Now let us say this is the address 1, which is here M1. Now if you see here 3 addresses, all right, and here there is the code for, or opcode, basically that's what we say, opcode for, let us say, addition, which is a particular bit pattern. Now, what our Turing machine can do, that in another tape it can fetch the contents of this address 1. How will it do so? Because you see, this is a bit pattern, and therefore, this of course goes to infinity, maybe on both directions. So, it looks for this pattern in the places, in those places where addresses could be stored. See that addresses are stored flanked by a sharp symbol and a send symbol, right. So, it will look for such strings in this tape and compare with this, right, bit or symbol by symbol. If they match, then it knows that it has reached the correct address, and then it can copy the contents here, right, in another. And similarly, it can, so basically what I am saying is that it is not difficult to see that fetching the contents of some specified addresses can be done fairly easily in this way. And now, what does opcode addition involve, executing that? It would just involve that adding this and this, if the contents of address 1 is here, contents of address 2 is here. So, essentially we need to add, and you can imagine that depending on whatever is the opcode here, the Turing machine, which is of course is going to be a big thing, it will go to a particular part of its. So, after all, opcode is again a string. The machine can decide, to go to a part of its machine's program, or after all, a Turing machine can be seen as lots of states, and in each state we are being told what is to be done. So, it goes to an appropriate part of itself where these operations will be carried out. Essentially, the operation what for addition is add this to this, and maybe the result of the addition we may, we can carry out that addition in another tape, right, and that addition is placed here, contents of the result of the addition. And now, the last part of this executing this simple instruction was to store the result in the address or in the cell whose address is address 3. Again, what we do is we will be scanning the memory tape. The Turing machine will scan the memory tape. It will find out where this match is occurring, right. Again, remember that strings which are flanked on the left by sharp symbol and on the right by send symbol, these are addresses, and when it finds, then after that send, it should place this one. Now, of course, it might mean creating space or squeezing some space, but all those are simple operations. By now, you should be convinced that they can be done. So, after that, it should carry out the next instruction, right. So, what would the next instruction, where will the next instruction be? Next instruction will be also there in the memory somewhere at a cell whose current address is the contents of the PC. So, basically, if PC was, PC you can think of is somewhere again on some another work tape or something with the program counter. So, now these are all some tapes, but this PC is program counter contents here. Now, normally what we mean is, unless the program counter value changes because of the operation of the previous instruction, we will add, that is what we say, add 1 to the PC, which really means go to the next instruction. So, again you look for this address between sharp and send, wherever you find it, skip the next contents part, go to the next thing here, right. So, whichever is the way, either we can say physically that the instructions will be one after another on the tape. So, if you just carried out the instruction corresponding to this address or contents of this address, for the next you need to, the address will be given here. So, that you copy and that will have the correct PC value. That is what you do after this, and then from there, from that address you fetch the next instruction in this tape, and that then you will be updated, the Turing machine will be updated to carry out the execution or the simulation of the execution of the next instruction. So, this is at a very gross level I have described that to you, or I have tried to convince you that it is not difficult to see that a simple processor can be simulated by a Turing machine, essentially simulating each instruction of the this simple processor program in an appropriate manner. Now, therefore, what we can say that Turing machines are of course fairly powerful in the sense that they can do all that our ordinary or even extraordinary computers can do. And when I say that it can do whatever computers can do, if we want to, if we want to work on this statement, in the sense if we want to find out what are the limitations of this statement, in the sense that can Turing machines do everything that you might think of doable, or it has its limitations. There we need to be a little careful, and therefore, we will come back to the context in which we operate, and that is recognition of languages. Recall that a language is some subset of finite strings over an alphabet, and let us say the alphabet, this is the alphabet of languages, under consideration. And now we may ask a very simple question, that does some Turing machine exist to accept a language that we choose. Let me put it slightly, this is not very nicely put. The way we would like to say is that, you see, there are a language over sigma is of course a subset of sigma star, right. So, the focused question is, given any L which is a language over sigma, and you can ask this question: does there exist a Turing machine to accept L? So, in other words, if you see, what we are really saying is that we are asking the question, are all languages over sigma recursively enumerable? Right? That is the focused way of asking about the power of Turing machines so far as language recognition is concerned over some fixed alphabet. Remember, just once more, the definition of recursive enumerability: we say a language is recursively enumerable if there is a Turing machine to accept that language. And the question that we are asking is that there are so many languages over sigma star. Do you have, for each language L, do you have a Turing machine M such that L is the language accepted by this Turing machine? Of course, different Turing machines will accept different languages, that is fine, or the same language may be accepted by several Turing machines, but given a Turing machine that accepts a specific language, and we want to know that the class of all Turing machines, when we consider the languages they accept, the languages, the class of languages accepted by the class of Turing machines, does that class exhaust all languages over sigma? Right? So, this is the question. And answer to this question is no. So, there are, in other words, what we are saying, that there exist languages over sigma which cannot be accepted by any. All right. You can see that if we prove this statement, then we have proved limitations of what Turing machines can do. So far, I have been trying to emphasize that Turing machines are very powerful objects or devices, in the sense that they can carry out all kinds of algorithms. And as is the philosophy of this course, we would like to understand the power or limitation of the power of any device that we are considering. So, in particular, we want to know that what is the power, or what is the limit up to which Turing machines can be used. All right. So, this proof of this statement, these two are, this statement that there exist languages over sigma which cannot be accepted by any Turing machine, proof of this statement is by something called a kind of argument which is called diagonalization. So, proof is by diagonalization argument. This is a very powerful style of proof. Now, you know some proof strategies like induction, um, proof by contradiction, etc. This is a special kind of proof by contradiction, and some of you might have seen the proof that there cannot be a bijection between the set of natural numbers and the set of real numbers. That proof typically that we know of is by a diagonalization argument. I would like to explain the diagonalization argument first by means of a simple but a fairly powerful proof of. Now, what I'll prove is this statement, that there cannot be a bijection between a set X and its power set which is normally denoted as script or P of X. Now, and we read it as power set of X. Now, what is the power set of X? So, Px is by definition set of all x1 such that x1 is a subset of X. Okay. So, power set of X consists of the set of, or power set of X is a set itself, I mean as the name suggests, and this set contains all subsets of X. So, in particular it contains the empty set, because empty set is a subset of X, as well as the X itself, because X is again a subset of itself. What this statement says, that between X and Px no bijection is possible. What we are trying to do? Let me just say it here. Example, diagonalization argument. Our diagonalization argument will prove this statement, which is of course same as that statement. Now, as I said, the diagonalization argument is also a kind of proof by contradiction, and any proof by contradiction starts by assuming the negation of what you want to prove. So, I should write here between X and Px no bijection is possible. That is your statement which you would like to prove. So, negation of this statement is that there is a bijection between power set of X and X, right. Assume that there is a bijection between X and Px. Let the bijection be F, and this F maps x to Px. Being a bijection, of course, F inverse also exists and F is 1 to 1. Now, what we will do is we define y, which will be also a subset of x. And the definition of y is as follows, that y consists of x in x, right, such that x is not an element of fx. Right? This looks a very innocuous statement, but it's a very interesting statement, because we will see how it manages to, this definition itself, how it manages to prove this very general result. All right. So essentially, how we are defining y, this capital Y, we are saying, look, an element of x will be in this set y if that element is not an element of the set or subset of x to which this small x is mapped to. This is what it is saying. Right? Now you can see clearly y is a subset of x, because y by definition basically some elements of x. So capital Y is a subset of x. Now, since it is a subset of x, map F will map it to, of course, some element. No, x for every x we have others. But you see, because it's a bijection, F is a bijection, at this, remember, this F is from this set to the power set. So since F is a bijection, for every element of this set, there would be some corresponding element of x, which, all right, is the map of the taking that element from here. In other words, so far as our purpose is concerned, again, y is a subset of x, since F is a bijection. Therefore, it is an onto map for its range, right? And of course, the range is the whole power set, and in the range y is there. So there exists some, let us say, x prime such that f of x prime is this set y. So I want to emphasize again that the existence of this x prime is because your f is an onto map on p of x, and capital Y, which you have defined in this manner, is a subset of x, and therefore it is an element of power set of x. And since f is an onto map on this set, there would be some element of the domain. The domain, of course, is the set x itself, capital X, some element x prime of an element of x such that f x prime is y. All right. So this is straightforward from the use of or definition of bijection. And now consider the question is x prime an element of y? Right, x prime is a specific element of capital X and y is a subset of capital X. So, it is a meaningful question that is this element an element of y. Now, suppose there are two possibilities, either x prime is an element of y or it is not an element of y. So, we are taking the first situation, suppose x is an element of y. So, now what is it saying? That remember we are saying since x prime, right, we are asking this question, is x prime an element of y? So, x prime, assume this, so x prime an element of y, which of course y by definition is f of x. So, I have x prime is an element of f of x prime, but if x prime is an element of f x prime, it can't be in the set y, because in set y you are only choosing those x's which are not elements of the set that x is mapped to by the bijection. So, this really implies that x prime is not an element of y. Right. So, starting from the assumption x prime is an element of y, we are getting to the fact or the conclusion that x prime is not an element of y. So, this is a contradiction. So, therefore, this supposition is wrong. The other, what is the other supposition? That x prime is indeed an element of, is not an element of y, right. Here we assumed x prime is an element of y and here we are saying x prime is not an element of y. Capital Y is by definition f x, right. So, therefore, we have x prime is not an element of f of x prime. Now, if x prime is not an element of f x prime, in that case you just look at this definition for y, this implies that x prime is an element of y. Now, here again the situation is, starting from this supposition we come to the conclusion which is just the negation of that supposition. So, there are only two possibilities, either x prime is an element of y or x prime is not an element of y. In both cases we are reaching contradiction, which therefore means that our original assumption that there is a bijection f between the set x, capital X, and its power set, that must be false. So, this whole thing implies f cannot exist, and therefore, we have proved that there is no bijection between x and its power set. All right. If you see what is really happening in this proof, the crux of the proof is in the definition that we made for y, and this definition made sure that no, so basically the definition made sure that y cannot be the map of any element of x, right. This is what we did. Now, this statement that y is not or cannot be the map of any element x, you may think of, I am just trying to explain how did you get to this definition, and because even what our Turing machine context will use similar arguments, we need to be clear about the way these proofs, diagonalization proofs work. So, this is something you are trying to prove, that construct some y such that this y cannot be the map. What was the map we said? F, the bijection map of any element of x. So, basically we wanted to show that take any element x of, and we wanted to ensure that f of x is different from y, right. Now, these are two sets, right. F of x is a set because f maps, so f of x is a set of elements from x, and this is also a set of elements of. The way we achieve for a particular, so here again consider a particular x, let us say x1, and we want to ensure this condition that fx1 is not same as y. So, this statement will be correct if for every element x1 we manage to do this. Now, two sets are unequal, two sets can be unequal because either this has an element which this does not have, or this has an element which this does not have, right. That is how we can say two sets are not same. So, you can imagine the witness of this statement will be an element which is in the symmetric difference of these two sets, right. That is, which is that element which is either here and not here, or which is here and not here. An interesting thing that we did, that we made x1 itself to be that element, to be that witness. So, let us write this sentence fully. Witness of this particular statement will be an element which is in that means all the elements which are in fx but not in y union symmetry. So, basically what is this saying? That this part consists of all elements which are in fx1 but which are not in y, and this consists of all elements which are in y but not in f of x1. So, now this entire set, if it is non-empty, that would mean, so this non-empty would imply this particular assertion that these two sets are not same. And the way we have defined this set y that we make x1 to be that element which is in the symmetric difference, right? How? Because you take your map, right, and see what x1 gets mapped to. So, this is a particular set. So, just call it Z, right. So, fx1 is of course a subset of capital X which we are calling Z, right. Now, this element, take this element x1, we are asking this question, is it in Z, right. If it is in Z, we will not put it in Y, right. So, in that case, if x1 is in f of x1, in that case x1 will be here, but not in here, because by this definition, since x1 is an element of fx1, will not put it in Y. So, this set will be non-empty because x1 will be there, or if x1 is not an element of fx1, then we will put it in Y. So, this part will be non-empty. In either case, x1 is the witness of this. So, we are taking every element and making it a witness of the fact that our constructed set is different from that subset of X to which x1 gets mapped to by our assumed bijection, and thereby we are proving that this particular statement is true. All right. So, again in summary, what is the summary of what I am trying to say here? If you see really a diagonalization proof, you will see it is trying to prove non-equality maybe of two sets, and this non-equality, like here we said that we tried to prove whatever be the statement, that assertion we could break it down to maybe an infinitely many simple assertions, like here that for any element, take an element x1, make sure that fx1 is different from y, right. And each one of these you ensure in defining the diagonal set. This y will be called a diagonal set. All right. So, we will see, as when you see for the first time such an argument, it looks complex, but if you go back and examine it once more in the light of what you wanted to prove and the basic strategy of the proof. So, you wanted to prove in this case that there is no bijection between a set and its power set, and your proof idea was assume there is a map, and then you constructed a particular subset of X such that it was not in the range of F. So, by that how did you do that? That this Y is different from the map of every element. So, all these conditions one by one, or conceptually you can see that for this condition x1 is the witness, for another, let us say x2, this x2 itself will be the witness, and so on. So, let me just complete that in this case, that element which is the witness okay. So, this is an example of a diagonalization proof. This is a fairly complex proof if you are seeing it for the first time, and it is a very powerful, as at least this particular example proof of diagonalization makes a very powerful statement. We did not make any assumption about the set X, capital X, whose power set we are considering. This X could be finite, could be infinite, and even in infinite we are not saying that it is denumerable or not. So, any set, for any set, the statement stands that there cannot be a bijection between that set and its power set. Okay. So, now what is the statement that we would like to prove in this course about Turing machines is by this method. First statement that we will prove is that there are, so this is what we will prove, that there are non-RE language. Again the proof will be proof by and let me give you the proof first of all from a very overall point structure. First of all, we will see that our case is simpler than the previous one in the sense that here everything is, at least our Turing machines, the class of Turing machines will be enumerable. So, what I mean by that is I can line up all possible Turing machines, all possible Turing machines to accept languages over sigma. So, this all possible Turing machines to accept languages over sigma, they can be kind of lined up. That means, what I mean is I can, the word is enumerate, okay, which is a technical word, but think of this way, it is possible for you to conceive of all these Turing machines to be in some sequence, M1, M2, M3, M4, M5 and so on, right. And each one of these Turing machines accepts some language. So, the language accepted by this is of course LM1, this is LM2, this is LM3 and so on. And now, you want to prove that there exists non-RE languages. So, if a language is RE, to accept which is in this, which is a language over sigma, then this has to be one of these languages. Is it clear? Because these are the only Turing machines which will accept languages over sigma, and these are the corresponding languages which are recognized by each of this machine. So, essentially these are all the RE languages which are over the input alphabet sigma. Now, in the same style, that the way we created here a y and made sure that that y is different in some way, in our way, particular way, what we are going to do here is to define a language, we will call it LD, such that LD is not LMI for any I. So, we will ensure, we will define a language LD and ensure that LD is not same as for every I, right? Once we manage to do that, if I can manage to do that, then that would immediately imply that LD is not RE. Why? Because had it been RE, this would be one of these. So, in particular, let us say had it been RE, it may be recognized by some M star, which is somewhere in this lineup. So, let us say this machine MJ, suppose it, if LD was RE, then there would have been a machine in this enumeration of all Turing machines to accept languages over sigma. Let that machine be MJ. The corresponding language would be LMJ. But we would have ensured, since we are doing it for all I, we would have ensured that LD is different from LMJ, and thereby we prove, again by contradiction, that LD is not RE. So, two things that I need to do, which we will do in the next hour. First of all, prove this, that Turing machines which accept languages over sigma, that class of Turing machines can be effectively enumerated, which means I can line them up one after another in some ordering. So, I can talk of ith Turing machine, I plus 1th Turing machine, nth Turing machine in that ordering, and if at all there is a Turing machine to accept a language over sigma, that will come somewhere here in this lineup. And then I would define this language LD, which by definition will make sure that LD is different from all these LMI. And of course, our LD will, the way we will do it, of course, it will be a language over sigma, and therefore, LD is not an RE language over sigma. Okay. This is for a fixed alphabet sigma, we will carry out all this discussion.